Hi, welcome back to this video series on program synthesis. Today I will show you how to synthesize the integer division problem using program synthesis techniques. In the previous segment, we derived automatically a function f, right, which was performing for us a by 2 power k. But we assumed that our a was greater than or equal to 0, or in other words, we assumed a was an unsigned integer. In this segment, I'm going to talk about 2's complement number, like or signed integers. Okay, so here we assume a can be negative, right? A can be below 0, or a can be greater than 0, so or greater than or equal to 0, right? It can. So in this case, how do we synthesize a program from existing operators other than the division operator? Of course, we don't want to use the division operator because it's too slow on many machines. How do we handle that problem? One natural question that may come up is that why not just use the same technique that we used in the unsigned case? Well, let me explain the problem though. The unsigned case works correctly even for signed ones if our a perfectly divides the denominator 2 power k. Okay, let's take it simple by just putting k equal to 1, right? So what we are saying is that if 2 divides a perfectly, right, in that case we can use the right shift operator as we did during the unsigned case. For example, if the number is say -4, okay, what is -4 in binary? -4 in binary, let's assume we have only 4 bits, okay? We start with -8, right? This is -8, and then we have to have +4, okay, and a 0 and a 0, right? This is -4, okay. And what if we want to compute -4 by 2? Okay, -4 by 2, as we know, is -2. So we can do right shift of a by 1 position, right? This means that our new pattern will be this 0 will go away, right? So we have a 0, we have a 1 here, and then a 1 here. But since it's the negative number, so remember this is negative number, so we are going to do arithmetic right shift. Okay, in C there's something called arithmetic right shift. In Java you have to use a different symbol for arithmetic right shift, but in any case I'm only talking about the C context. So this is arithmetic right shift. What it does is when you do right shift, the leading most significant bits are filled by just copying the original most significant bit, which is in our case 1, right? So the 1 gets copied here, the 1 gets copied here. So we have this, okay. And now what is the value of this? Well, this is -8, this is +4, which is -4, -4 plus 2, a is -2. So this is the value of a right shift by 1. So we get what we wanted, right? We divided a by 2, a is -4, divided by 2 is -2. This works. However, let's consider this scenario. Let's consider the scenario of, let me clear this so we get some space. Let's see. What if our a is say number 3, and we have to analyze how the right shift works for us, or will it work for us? Okay, so I'm going to do this now with the scenario of a equal to -3, right? So what is a equal to -3 in bit patterns? Let's assume we again 4 bits only, right? So we need -8, right? And then we need a +5, so we can get a +5 from this, right? So this is basically -3 in binary, right? -8 plus 4 is -4, -4 plus 1 is -3. Okay, so this is -3. What if we do a right shift of a by 1 position? Okay, Well, let's look at that. When we do this, this 1 will disappear. So we'll have 0, we have 1, and we have a 1. And again, since it's a negative number, we just have to transfer the most significant bit from the original number. So we have this number, which is nothing but -2, which is clearly wrong because -3 divided by 2. Let me use a different notation. -3 divided by 2 in terms of integer division is actually -1 in, I must say, in most programming languages that I know of. Okay, actually C and Java does this. Okay, as an example, some versions of Python actually will give you -2. Okay, this is really weird. Just keep in mind, I'm not talking about Python, so this division is not relevant for the discussion that I'm going to do. So forget about this. Okay, I'm only interested in the case when just remove the decimal parts. That's basically what I am after. Okay, so clearly right shift by 1 doesn't work when we have a number that doesn't divide. That's not divided by 2 power k properly. Okay. So what shall we do now? Well, we can ask the synthesizer to help us, because we have this nice machine that can help us to synthesize programs. So let's jump there and see whether we can get the synthesizer synthesize a program for us. Okay. So what I'm going to do is I'm going to show you starting from simple scenario of dividing it by 2 first, and then 2 square, and so on. So I'll take step by step. So what you're seeing in a moment is basically this is basically your synthesizer, which is going to synthesize a program for us, right? So it synthesized this program for us. So let me explain what it is in a moment. So I will first show you the program, so it makes quick sense. We have seen this several times, the grammar construction, so I'll quickly go through this, right? I'm saying you're allowed to use all of the bitwise operations other than multiplication and division pretty much. And here is the expected behavior, right? I want to synthesize a function called division by 2, which will take a number a as an input. The output should be same as a divided by 2. Right, this BVS div is part of the specification. Okay, it's not part of the synthesis, by the way. The synthesis doesn't have B div. You can see here nowhere in this grammar I allow BV div. Okay, so what I'm going to do now is you can also imagine this is an oracle, right? It is used as an oracle under the hood to compare whether the div2 matches the specification. Okay, this is specification, this is implementation, and we would like to synthesize this implementation, which is consistent with this. Okay. So what I'm going to do now is to show you how to interpret this data that is coming out, right? So the program synthesizer synthesized the division by 2 logic, and it reads as follows, right? It says the function f that it is synthesized is nothing but a little bit complicated than the unsigned case. So what is the inner statement is a bitwise logical shift right. So we have a number a. We right shift by how many? 4 plus 2, 6, 7. Okay, so by the way, I programmed it only for a byte, right? That's why I have 7 here. Okay, we are right shifting it by 7, and then what are the things we are doing? We are adding a to it, right? So a gets added to it, and then what are we doing? We are doing a shift right. Let me write this as a logical, right? And then we're doing a shift right by 1 position. Okay, so the whole thing gets shift right by 1 position, right? So this is the synthesized function from the synthesizer. Okay, let's see whether we can make sense out of it. Okay, What if my A is say, well, I'm going to do a simple trick now. Instead of working with 8-bit, which is a lot of data to work with, I will work with a much more smaller, and then we can generalize it to 7-bit, rather 8-bit or 16-bit, 32-bit, and so on. Okay, so I'll first take a simple scenario where assume we are only working with 4-bit numbers, right? So what if our what if our A is like say -3, as we discussed earlier, right? What do we expect the answer to be? The answer to be -1. So can we confirm this? We have -3. First step is to shift right. What was this called? Shift left. Logical left. But remember, we are not dealing with 8-bit. We are dealing only with 4-bit now. So so maybe we can say, well, instead of left shift by 7, we should be now left shifting only by 3, because our original bit vector size is 4. Okay, so maybe I should avoid -3 for a moment. Just make it different to avoid any confusion with that 3 and this 3. So I'll take my A to be -5, right? And I'm going to do a left shift by 3 positions. So what is -5 in bit pattern? -8, and then I need to add a 3 to it, right? So this is the bit pattern of A, -5. And I'm going to do a logical right shift by 3 position, right? So what will happen? So basically I'm replacing this by 3 here, right? Because my bit vector size has been reduced. So when I do a logical right shift, now I'm get rid of all these 3, and my new value will be, what will be my new value? My new value will be, okay, so this is, oh, I was trying to say 3. My new value will be, so I have 1, 0, 1, and I'm going to get rid of the last 3 least significant bits. That means I will be end up with 0, 0, 0, 1, right? Essentially, I get rid of these 3, right? They're gone. So now I have a number 1, which I add it to A, which means my A becomes -4, okay? And then, okay, let's write -4 in binary. What is -4 in binary? We have 4-bit representation, so it must be this, right? This is -4. Okay, so we are done with this part. What is the left? What is left for us is to do. This is shift right by arithmetic right shift. We have to do by 1 position. Okay, so here is the data that we got, and now we need to do arithmetic right shift by 1 position, right? Okay, now we have to be careful. When we do arithmetic right shift, we get rid of the rightmost bit by 1 position. So we have 0, 1, and 1. The most significant bit will be also 1 because of unsigned, because of signed representation. So what is this now? What is this? This is nothing but -2. Okay, and does it make sense? Well, it does make sense. What is -5 by 2? Well, as I said earlier, we divide and get rid of the decimal part, therefore it must be -2. And we did get this. So the synthesizer appeared to be, of course, correct, because we formally verified that this is equal to the regular division, which is built inside the assembly solver. So what I'm going to do now is just clear this thing first. And I will now show you the scenario when I'm going to try with 4, 6, 8, and 16, and then we can generalize it by 2 power k, right? That's my goal. So let's try with 4. Okay, 4 may be more involved. Okay, but the synthesizer does a good job. I was really surprised. I never used it, but it seems to be very good in finding programs so far. There are scalability issues, but if you know how to scale it properly by not overwhelming it with large bit size, I deliberately chosen small bit vector size just to get the answer I need, right? Okay, so here is the program that is synthesized for 4-bit let me clarify what I mean. Synthesis for division by 4. So basically, we are dividing the number a by 4. So let's continue this and see some patterns. Okay, maybe I will just show you very quickly. This is for 4. Okay, let's run this. And then I will show you 8 and 16, and then we can easily generalize it for division by 2 power k from that. Although in theory it should be possible for the machine to generalize, but I felt that it was not scaling for my grammar, so I decided to do it by induction myself, which is not bad at all, right? So I will now do 8, right? So it's easy to see the structure overall, and very quickly we can generalize it. So this is now working on division by 8, which means 2 power 3. Okay, and then I will show you division by 16. I'll stop there. Okay, so we got division by 8 done. Let's look at division by 16. Okay, so hopefully, what did I do? Maybe I made a small mistake in my division by 16. I have multiple programs which are more or less the same, just for demo purpose. So, I declared it by wrong name. Sorry for that. Okay, so we need to see now for 16. Okay, the program is computing a by 16, and it will give us an expression like this, like the one that you're seeing here for 8. Okay, so as I said, it has computed successfully a program which we can use for analysis. And actually, as a matter of fact, the structure is very, very similar, independent of whether we are doing division by 8 or 16. Let me run the 8 one more time. Okay. What is interesting though is that we can generalize it to any k when we want to divide by 2 power k. Let's see very quickly. Hopefully it will come. Yeah, it has come. So this is for division by 8, right? So if we look at this division by 8 and division by 16, they're pretty much similar, right? You have here right shift, here also right shift. Here is add, here is add. Here is the logical right shift. Here is also logical right shift. And the only difference though is the amount of the amount involved in doing the right shift, right? I spent some time on I will generalize it now for you. Other than that, the structure remains the same. So let's think about it. What's happening when we do a shift by? You know what? Maybe we should just start also with 4. What we have done so far is 16 and 8, and 4 will be also good to have. So what we are trying to do is simple, actually. When the number x is less than 0, or number a in our case is less than 0, before we do the right shift, right? What we are trying to do is, excuse me, we are trying to add some amount so that the negative numbers are actually rounded toward the 0 direction. That's what we are trying to do. The whole objective of adding something to a is to just take care of the scenario when a is less than 0. Otherwise, it's not rounding properly. It will go it will go away from 0 instead of coming towards 0. Okay, that's basically the objective. So we can easily now generalize it. Let's look at the last part of the expression. Okay, it's number 2, right? This is 2. When we divide it by when we want the program to divide it by 4, the amount of right shift is 2. Okay, which makes sense. And if you now look at the scenario when we want to divide it by 8, it is right shifting by 3. So this is getting there, right? If you wanted to divide by 16, you can see that it is doing the right shift by 4. So it's basically the 2 power of that number, right? That's basically, this is 4, right? This is 4, and this is 16. So essentially you're taking the size of the number minus 1 in terms of 2 power. Okay, so basically if you know if you want to divide it by 16, we know 16 means 2 power 4. Just forget about 2 power 2 for a moment. So it's basically 4 minus 1, which is 3. And the same thing here, right? 2 power 3 is 8, and power is 3, right? So just remove a 1 from it, so you get, oh yeah, it's exactly this here, right? So that's basically the idea. That did I say something wrong here? One moment, let me clarify. So we can, yeah. So I think we're okay. So we have division by 4 here, and we are actually shifting it by 2. Okay, so this is basically it. We can easily generalize this behavior for any number k. Okay. And what about the inner parts? Okay, the inner parts is also generalizable. We do shift right, logical shift right. How much are we shifting? Like when we want to divide it by 4, we are only doing it. Let's do the inner part. The innermost part is actually the arithmetic right shift. Okay. The arithmetic right shift is just by 1 position when we divide it by 4. When we divide it by 8, it is 2 position. When we divide it by 16, it is 3 positions. So this is also generalizable. So what I'm trying to say is that we can actually get a general expression for division by 2 power k. That's basically what we learned. Okay, so to make the long story short, what we synthesized is basically this particular expression, right? The expression that allows us to compute f of a by doing something as simple as this, right? If you want to compute a by 2 power k, all you're doing is essentially you are basically, in the innermost statement, you're doing you're doing a right shift, right? This is arithmetic right shift. Let's see, for 4 we are doing only 1 here, right? Okay, so what is that we can say? For 8, we can say it's just 2. Okay, that means you're dividing it by what is it we are dividing it by? We are dividing it by we are writing it by 2 power 3, right, which is 8. But then we just take the power and subtract it by 1. So power minus 1 essentially. So that should be the constant that goes here. Okay, so that's the constant that we fill in here. The constant is this number, which is different for different k, right? And then the next level is basically adding this to a. Okay, and then we do a shift right. Okay, this is arithmetic, by the way. Okay, well, yeah, we add this, and then we do logical shift right of this expression by another constant. Okay, this constant is also differing based on the k size, right? This here, this is 6, so we do 6 here. Here we do when we divide it by 4, we do 6. Here we do 5, and here when we divide it by 8, we do 3. So this constant is also another number that we need to plug it in properly. What is this left? We're doing logical right shift, right, by another constant. Okay, so we have to fill up these 2 constants. Okay, these 2 constants are the constants that are sort of a function of the k that I was talking about. You know, the goal is, remember, the goal is to divide a by 2 power k, right? You want to divide a by 2 power k for different k values. Okay, so the program synthesizer was, at least not in my case, was not able to handle different k's. So I decided to run it for k equal to 1, 2, 3, 4, and so on, and then generalize it. Okay, that's what I'm doing. And then the final step is doing a shift right. We have to talk about this one. by another constant. Okay, so we do a shift right, this time arithmetic shift right by another constant. So if you do this, basically you are able to compute f of a, which is basically a by 2 power k. Okay, so that basically wraps up my my discussion, but I can actually write this in a more structured way. We can just fill up these holes, right? At this point, I just left the holes for your thoughts, but I will be able to easily fill up this because this is clearly consistent pattern. Okay, so let me write it now for a moment. One moment. So what is the learned model? Okay, the learned model is we tried different case, right? And we can easily see that we do something like this actually. At a high level, if you want to abstract, our f of a is nothing but some a plus, well, this is the a that they gave to us. We take the number 1, we left shift by k. Okay, actually these two expressions are the same. Minus 1, this expression is the same as what we synthesize actually, and then we right shift this by k positions. Okay, this is basically the idea behind division by 2 power k for the scenario when a is less than 0. Okay, otherwise it's enough to just take the a and do a right shift by k. Otherwise, this is for a less than 0. What if our a is greater than or equal to 0? That we know, that's easy, right? We just have to do the regular just do like this, right? Regular right shift. So this is basically what we learned through the synthesizer. Let me go back to the code here. So the difference is basically in the amount of constants values that we are doing the shift. Other than that, literally there is no difference between the expressions, right? It's the same structure. So it's really amazing that the program synthesizer actually came up with expressions for division by 4, 8, 16 in a consistent way. Let me check my division by 16 for a moment. Okay, so yeah, clearly I think yeah, 16 is 2 power 4, which means fifth bit, and this is the right place where it's on. This is x means x, right? That's perfectly fine. Okay, in hex it's 10. All right, so 16 is this, and what about 8? 8 is let's see, yeah, 8 is 8, regular 8 in hex, no difference. And then what about 4? 4 is division by 4. So it simply works, by exploring this grammar and comparing against this spec, it was able to come up with expressions for us. Okay, the beauty though is that we don't have, let's say, for example, oops, let's see, division by 4. When we divide it by 4, we don't want to see the division operation, right? And we can confirm that that's the goal of our synthesis. It takes a few minutes. Okay, yeah. So there you go. So as you can see, there is no division here. It's shift right, add, logical, shift right, and shift right. That's all. And was able to come up with these values also, right? These constants are already picked by the program synthesizer to meet the goal of the synthesis. Where are those constants coming from? They are coming from our statement that we need this division variable to the division function to match up with the specification. This is the specification, okay? And it was able to fill in those place values, right? Values for these variables in such a way that the synthesized division function matches the specification. All right, that's basically it. And I hope you are able to understand the purpose of it. Okay, well, one more thing. The constants actually is not coming from there. The constants are coming from here. I forgot to tell you that. That's the shift left, shift right. We placed a shift amount, how much amount to shift. Remember, if you have an 8-bit number, you cannot shift more than 7. That's why I have to spell out numbers from 1 to 7. Okay. All right. I didn't introduce a constant variable, by the way. There is something you can introduce here as constant. Then it will put some numbers in those places instead of expressions. Anyway, that's not important at this point. What I have hopefully conveyed to you is how to synthesize division by 2 power k when the number itself is signed. Okay, thank you. That's all.